Hello, everyone. My name is Junhyoung Lee, and I am a research engineer at Easywith. Today, I would like to introduce our work, Nonlinear Color Transfer via Learnable Bezier Flows. Color transfer is a technique designed to seamlessly implant the color distribution of a style image into a source image, all while preserving the source's inherent scene structure and perceptual realism. Rectified flow fails to accurately reconstruct colors in flowers, skin tones, and 3D rendered objects because it restricts the source to target transport path to a strictly linear trajectory. We propose Bezier flow, which utilizes curved paths instead of straight lines to flexibly transport color distributions, successfully resolving the reconstruction problem. Let's look at how color transfer technology has evolved. Classical CT often fails to fully adapt, leaving behind source colors that shouldn't be there. Moving to deep learning, DSD struggled with color bleeding artifacts. Then there's Neural Preset, which delivers great quality but heavily relied on domain-specific supervision, such as professionally crafted lookup tables. And flow-based model, like ModFlows, fall short. They aggressively overcorrect, blindly forcing the target style and destroying the natural look of the image. Now, I would like to introduce Phase 1, Learnable Bezier-based nonlinear transport. In this phase, we learn a Bezier path that maps each image into a shared latent space. To do this, we use a control point predictor. It generates customized control points optimized for each unique pair of images, which creates a truly nonlinear path. This Bezier path then derives a velocity field over time, and the entire process is optimized using a flow matching loss. As a result, we successfully build a dataset where each image is perfectly paired with its optimized flow parameters. Now, the objective of Phase 2 is to train the encoder so that the network can instantly predict the appropriate nonlinear flow, even when given an entirely unseen image. To achieve this, we use the flow dataset constructed in Phase 1 as our ground truth for supervised learning. However, a single shared encoder lacks the capacity to capture the sheer diversity of the Bezier flow. To solve this, we introduce a mixture of experts mechanism, extracting rich feature maps packed with spatial details and color context. While baseline models either fail to apply the style color, suffer from color bleeding, or overcorrect by aggressively forcing the style, our method harmonizes the style colors with the content on a global scale, delivering natural and visually consistent color transfer results. Furthermore, ours achieved the highest aggregated score, which simultaneously reflects both content and style preservation. In our evaluations on the media art dataset, it demonstrated outstanding aggregated scores and Lipschitz scores, even within complex and highly artistic domains. When we used a fixed control point, the model was forced onto a rigid, predetermined trajectory, which resulted in high training loss and limited flexibility. In contrast, our approach utilizes a dynamically learnable control point. By allowing the network to adaptively position the control point based on the source and style images, it successfully minimizes optimization errors. As a result, these learnable control points achieve significantly lower loss values, ensuring a much more precise and high-fidelity color transport. We also conducted an analysis of mixture of experts modules. We specifically integrated the MOE at locations corresponding to the style-relevant layers. ModFlows fails to preserve detailed colors, and NCT, without MOE, lacks color expressiveness. Incorporating the MOE significantly boosts color representation. This confirms that the MOE selectively and effectively modulates color features. In conclusion, we introduced NCT, a nonlinear color transfer framework that leverages Bezier flows to overcome the limitations of traditional linear transport models. By learning perceptually coherent trajectories through intermediate control points, NCT achieves significantly smoother and more accurate color transfer. Furthermore, the integration of the mixture of experts module drastically improves generalization, enabling robust performance even in high-resolution, texture-rich scenarios. Particularly on the media art, NCT consistently outperforms other baselines across most metrics. This explicitly proves our framework's robust generalization and visual coherence, even when handling highly complex artistic styles and intricate. Thank you very much for listening to our presentation.